Hello everyone. In this video, we will be discussing some numericals on welding. And this problem I have taken from a VTU recommended textbook author V.K. Bandari. We'll see the first question. So there is a problem which has showing some sketch. So it shows that a cylindrical rod of 50 diameter welded to a flat plate. So the cylindrical fillet weld is loaded eccentrically by a force of 10 kN acting at 200 from the welded gate. If the size of the weld is 20 determine the maximum normal stress in the weld. So for this particular sketch only, we need to solve the problem. So let me write the solution. We know that let h is nothing but throat thickness, which is nothing but t divided by root 2. So this formula I have taken from the design data handbook. Let us introduce two equal and opposite forces F1 and F2. You can able to see this is F1 and opposite direction we have one more force, that is F2, and which is acting parallel to the force F, and passing through the center of the rod at the fixed end such that F1 is equal to F2, which is equal to F. So effect of F1, or which is F whatever is to produce a transverse shear stress tau. So therefore the throat area A is equal to pi dh, where I know that the h is nothing but t by root 2 already from the design data handbook I have noted down, and the d given is 50. So area value I will be getting it as 221.8 mm square, that is 2221.8 mm square I will be getting from the throat area formula. And I have a transverse shear stress. The formula is F divided by area. So F is nothing but the force, applied force, that is 10 into 1000, because kilonewton to newton conversion, and the area is 221.8. So the transverse shear stress tau is equal to 4.5 newton per mm square I am getting. So now the effect of F1 minus F2, that is F minus F, is to produce bending moment M, and which is given by M is equal to Fn, that is 10 into 1000 into 200, that is 20 into 10 power 5 newton mm. For a circular fillet weld, section modulus Z is given by pi t d square divided by 5.66. So that is pi into 20 into 50 square divided by 5.66, that is 2.7752 6 mm cube I will be getting as section modulus, and the bending stress sigma b is equal to m by z, that is 20 into 10 power 5 27752.6. So after simplification I am getting bending stress equal to 72.1 newton per mm square, and the resultant or the maximum normal stress RB is equal to square root of tau square plus sigma b square, that is 4.5 square plus 72.1 square. So I'll be getting the resultant stress is equal to 72.24 newton per mm square. So let us move to the fourth problem. Again, this problem I have taken from the author V.K. Bandari. This is very important problem. So we will see, and it is an eccentric loaded welded problem. So the figure shows an eccentrically loaded welded joint. We need to determine the fillet weld size. We need to determine, and the given value is allowable shear stress in the weld is 80 megapascal. This is the allowable stress value. So first we will have a look on the sketch. It is a combination of parallel fillet weld and transverse fillet weld, and single transverse, and it is a parallel fillet weld where the length is given as 150 for the parallel side, that is for the x-axis. So both the sides 150, but we do not know what is the length of the transverse fillet welding side. So that also given, that is 200. So I can able to find out what is the total welding length. It is 200 plus 150 plus 150, and we have one load of 50 kilonewton, which is applied at a point somewhere away from the point of the welded has started, and the distance is 400. So we call it as an eccentric distance, that is E equal to 400. So now first we need to find out the center of gravity point, and later primary force, secondary force, and angle. All those things we need to find out. First let me write down the given data. So F is equal to 50 kilonewton, B is 20, so I will be writing the width and the length so that it will be easy for me. So this is B and this is L. So B is 200 mm and L is 150 mm, and allowable stress is 80 megapascal. So let me assume a small t is the size of the weld and a small h is the throat thickness. Already we know that from the data handbook we can take down the formula, that is t divided by square root. That is nothing but h formula. So the distance of the center of gravity g from the left edge of the plate x is given by x is equal to L square divided by 2L plus b. So I'll be knowing both the L and b value. By substituting in this, I can able to find out what is the x value. So eccentrically I can able to find out E is nothing but 400 plus 150 minus x. So x value is 45. So eccentric E is nothing but 505. So it is so clear that from this point to exactly this point is the eccentric distance. So that is 505 mm. And the polar moment of inertia of the weld. So throughout about center of gravity. So J equal to T divided by square root into B plus 2L whole cube divided by 12 minus L square into B plus L whole square divided by B plus 2L. Here B is known, L is known. By substituting these value and even T is also known. T is unknown. So we can able to find out the J value, that is 3468.3 into 10 power 3 T mm power 4. So the maximum radius of the weld GA is equal to R max, which is equal to square root of AB square plus AC square, that is square root of 100 square plus 105 square, that is after simplification we are getting it as 145 mm square. Now cos theta is GB by GA. So how I am telling it is GB by GA means, see, this is cos theta, it is adjacent side divided by hypotenuse. So adjacent is GB and hypotenuse is GA. So it is 105 by 145. GB it is 105 and GA it is 145. I have taken this value from this thing, from the trigonometrical calculation. GA value I got it. So cos theta I will be getting as 0.724. And the throat area of the weld A is equal to B plus 2L into T by square root. T divided by root 2. So after simplification I will be getting the throat area of the weld A equal to 353.63 mm square. So from the previous sketch, let me refer that and let me assume that two equal and opposite forces, that is F1 and minus F2, are through the center of gravity G, and which is parallel to F, such that F1 is equal to F2 is equal to F. The effect of F1, that is equal to F, is to produce primary shear stresses. So primary shear stresses tau 1 is equal to F by A, that is 50 kilonewton. So 50 into 10 power 3 divided by area 353.60. After simplification I will be getting the primary shear stress as 141.4 divided by T Newton per mm square. So the effect of F minus F2, which is equal to F minus F, is to produce moment Fe. So inducing secondary shear stress. So maximum secondary shear stress tau 2 equal to Fe divided by J into R max. So Fe 50 kilonewton, so 50 into 10 power 3 into R max, it is 505, and J value, let me substitute 3468.3 into 10 power 3 into T into 145. So after substituting I will be getting the secondary shear as 1055.6 divided by T. So the resultant maximum shear stress formula is tau mass is equal to square root of tau 1 square plus tau 2 square plus 2 tau tau 1 plus 2 tau 1 tau 2 cos theta. So it's a printing mistake. I am reading out. You can understand. Square root of tau 1 square plus tau 2 square plus 2 tau 1 tau 2 cos theta. So I know what is the value of tau 1 and tau 2. By substituting these value, I will be getting the value as tau max is 1162.1 divided by D. Already I know that the maximum stress, that is the allowable shear stress, is given in the question is 80. By substituting the 80 and equating it to 1162.1 divided by T, I will be getting T is equal to 14.5 mm. So with this video gets completed. Thank you.